In this, which is the second of 3 videos covering the topic of translations of functions, we're going to look at horizontal and vertical expansions and compressions. So in other words, there's a previous installment that covers horizontal and vertical shifts, and there's a third installment that covers horizontal and vertical reflections as well as identifying symmetry. So here we're only looking at horizontal and vertical expansions and compressions. Probably the most slippery of the various translations you're going to be exposed to. Let's talk about the notation that we're going to be using. As before, we're going to be using the letter C to represent a constant. And unless we say otherwise, we're assuming that it's positive. It's just so much easier to deal with it when you assume that the constant is positive. And we're going to start with horizontal expansions and compressions. We'll get to the vertical after we've looked at a couple of examples of this. Now, I would say that of the different translations you come across, probably the horizontal expansions and compressions are the most difficult. It's counterintuitive, number one, and if you have a function which has infinite support, it can be very, very hard to read when this type of a transformation has taken place. And so that's why when you look at the examples that we've prepared for you, we're using functions that have a finite support. In other words, a domain that has a finite length and a range that has a finite length. Now we're making a change inside the argument. If you recall, when you talk about function notation, f of x, and you have this quantity x in the parentheses next to f, the x, or the content of the parentheses, is what we call the argument of the function. And so if you want to make a function compress horizontally or expand horizontally, you're going to be using the constant c as a multiplier inside the argument. And so f of cx is what results in a horizontal expansion or compression. And what comes out from that, it completely depends on the size of c. And it's counterintuitive. And so we're saying that if you use a value of c which is greater than 1, you get what's known as a compression. And it compresses by a specific amount. It's the reciprocal of c. Likewise, if you choose a value which is between 0 and 1, you get an expansion. And it expands by a factor which is the reciprocal of c. So it sounds kind of similar, but in practice, very different, as you'll notice when we look at some examples here. Let's take a look at the first one. So we're using the same piecewise linear function that we had used in the previous video and in the third video in the series as well. And we want you to notice in particular that this function has a domain which goes from -8 to +8 on the x-axis. And it has a range which goes from -4 to +4. Now when you're looking at a horizontal expansion or compression, the domain is really what's of interest. You're not going to see any change in the range of the function. It's the domain which is going to change. And so take a look at the example on the right. We're using a value of 2 for the constant c. And so for f of 2x, many people their intuition would suggest to them that, well, it should expand by a factor of 2, but it's exactly the opposite. If you compare the domains, you'll notice that the function on the right has a domain which is half as long as the function on the left, the reciprocal of 2. Reciprocal of 2, of course, is 1/2, and so you end up shrinking the domain by a factor of 1/2 when you use a value of 2 for the multiplier. So again, look carefully at the function on the right. Notice the domain goes from -4 to +4 on the x-axis, and that is half as long as the function on the left. Next example. Now, I could not fit the original function on the slide at the same time as this graph here and have both come out as readable. So if you recall, the original function was supported from -8 to +8 on the x-axis. And if you look at this function here, it's supported from -16 to +16. And so the domain has increased in length by a factor of 2. It went from being 16 units long to being 32 units long. And you can see that the constant that we've used as a multiplier is 1/2. And if you stop and think, what's the reciprocal of 1/2? it's 2. And so the domain has grown by a factor of 2. And so again, if you compare these two examples, if you're using a value of the constant which is between 0 and 1, you get an expansion, as you see here. And if you're using a value of the constant which is larger than 1, you get a compression, which we saw on the previous example. Take a look once again. So a value of c which is larger than 1, as here we use 2, compression. A value of c which is smaller than 1, but still positive, so larger than 0, produces an expansion, contrary to intuition. Let's talk about vertical compressions and expansions. Now for the vertical case, the constant that we're using as a multiplier is outside the argument of the function. So in other words, c times f of x. And again, the size of c is important. We're still assuming c is a positive constant. We'll talk what happens later if it's negative, but if c is a positive constant and it's greater than 1, you get an expansion, and it's by a factor of c. And if c is a positive constant but it's less than 1, so in other words between 0 and 1, you get a compression. And that's very intuitive. This agrees with people's intuition fairly well. And what you want to pay close attention to in the examples which follow is the range of the functions, because that's what's going to be changing. So here again on the left we have the standard linear piecewise function that we've been using as an example. And if you look carefully, you'll notice that the range of this function goes from -4 to +4 on the y-axis. So the range of the untranslated or uncompressed, unexpanded function is 8 units long. You look at the function on the right, 2 times f of x, and you'll notice that the range has increased in length by a factor of 2. So the function on the right, the range goes from -8 to +8 on the y-axis, twice as long as the original function before this expansion. And in a similar fashion, if you use a number in between 0 and 1, you get a compression. And so once again, if you make the comparison between the two functions, you'll notice that the function on the right has a range which goes from -2 to +2 on the y-axis. It's half as long as the original function on the left. And you can see that we used a multiplier of 1/2, so no surprise there. Now the trick is combining all of these different things into a single example, and we're going to showcase that, but we have to talk about reflections first. So if you have any questions about this video, drop me a line. Otherwise, let's go on to the next installment and take a look at what happens when we have reflections.